So I don't think that you will have a difficulty here, because what I will do is just I use it the series and I just replace it the series. So now I have this integral. I have this integral 0 to infinity e power 1 over 2 exponential. We have a function, we call it gamma x. Gamma x is integral 0 to infinity e minus t power x minus 1 dt. And this is very similar to that. Just we needed to keep it that as a t, for example. Yes? If you change the variable from e to the t, so you can calculate the integral. So I want to evaluate the integrals. I'm continuing. So sigma n 0 to infinity, z n power 1, integral 0 to infinity. Now I change it the t to e. So dA t will be beta n plus 1 dAe. So dAe will be dAt beta n plus 1. I just replace it at the parameter. So let me to make it, let us simplify. So sigma n 0 to infinity. Everything is related to the n. I will set outside. So beta n plus 1 over 3 over 2. So you have just integral 0 to infinity t power 1 dt. And what is that? This is the gamma 3 over 2. This is gamma 3 over 2. By the definition, this is a gamma 3 over 2. Gamma 3 over 2 is 1 over 2. Gamma 1 over 2 is a radical p over 2. Finally. If you don't know how to find the gamma 1 over 2, first you needed to know that gamma x plus 1 will be x gamma x. This is the first code. So gamma 3 over 2 is 1 over 2 gamma 1 over 2. So using this property. And secondly, you needed to calculate gamma 1 over 2. What is the gamma 1 over 2? Sigma e minus t minus 1 over 2 dt. So it means that you needed to find this integral. Just change the variable from t to the, I don't know, some other parameters like kc. The integral will be transformed to the 2e minus kc squared dkc, you can see. And this is just minus infinity to infinity minus kc squared dc. This is a Poisson integral, so vector p. So I find that the integral which I needed, so now I can write the expression for the n. So the n is, so finally n is n minus, because this coefficient, I forget what was. The coefficient was 2p, 2m, 3 over 2, h cubic, yes, this integral. So So you know what is the beta? Beta is 1 over kt. So just replace it 1 over kt here. And keep it also radical and simplify the radical by radical. So that will be what is the lambda? Lambda is this h radical 2p m kt. Try just to from here. Just try to write it this in terms of lambda. It will be 1 over lambda cube. Just write it this lambda here. You will see that it will be reduced to that. So, and what is that? This is actually, you can write sigma 1 to infinity z n power 3 over 2. This is, we call it g 3 over 2z, Bose-Einstein functions. So n minus n d0, finally find that it's related to the cubic power of the inverse of the thermal wavelengths multiplied to the 3 over 2. N over V normally we write like an density, number density. You can write it that. So this is actually n minus n0 lambda cubic g3 over 2z. Another form of this equation. So you can repeat this calculation for the pressure, but for pressure you need one more step, is that you need first to take integral part by part from this term. You know the pressure minus kT 2p 2m 3 power 2 h cubic that was the pressure as I remember, yes? First time we remove it because we show that the first time is in the order of ln over n, so we said that it's. So you have to calculate this integral. So to make it this integral like g, like the function which I define it here, g nu z actually is sigma n 1 to n, z power n power nu. This is called Bose-Einstein functions. A Lerch function. General is a special class of the Lerch function. So this is a subclass of the Lerch function or Bose-Einstein functions. And especially when z is 1, g mu 1 is called Riemann zeta function. So it's one of the important functions in the mathematical physics. Riemann zeta function. It appears in several theory of theoretical physics. In several places you have Riemann zeta function in the field theory, in the statistical physics, and many places actually. You have the Riemann zeta functions. So this is the class of the function. So still you needed to also convert that to this. To convert that to this, you needed to first do part by part integrations. So we take the integral part by part. Okay, this is a part by part integral. Integral uv is uv minus integral v du. But you need to be very, very careful about when you take the derivative. This is a derivative with respect to the e, so this is the derivative. So what about the first term? You see that there is a first term up here and it's very, we feel not very good about this term. When limit e to infinity, e power 3 over 2, n1 minus z e minus beta e. What is that? Yes, one limit is infinity. This is 0. You can show that this is a 0 because of the loop dot rule. You know what's that? Limit f over g is limit f prime over g prime, limit f second over g, limit f. You can continue as much as you want. And what about the upper limit 0? Limit energy to 0 is e 3 power 3 ln 1 minus z e minus beta e. This is also 0. By many reasons. One reason is that when e is 0, this is logarithm 1. So logarithm 1 is 0. I call logarithm 1, this is ln, because logarithm, I call it this logarithm. It's a Napier logarithm. So this is the integral, and this integral I can calculate in terms of the Bose-Einstein function. So let me to compute the pressure. So one minus appear here, and that's good because can be removed by this minus. So pressure will be kt2p 2m 3 power 2 ht 2 power 3 and can I put the beta outside because beta is not related to anything. Also z, yeah? That's we don't use. Here we have, no, keep it as z. So will be e power 3 over 2 dE. You have a z exponential and you have one equal z exponential. I use again the geometric series. So will be z e minus beta e, sigma n 0 to infinity, z e minus beta e power n. Yeah, and this is all the coefficients. This is all coefficients. So do you want we can simplify or no? We just write it that, and later we will simplify. 4p over 3h cube beta 2m 3 power 2 sigma n 0 to infinity and integral 0 to infinity. Z power n plus 1. This. Look at that, that's the. What is this integral again? Again, you change the variable from e to t, like what I did before. Take t n plus 1 beta e and do the same as I did it in past. So you will have this coefficient. I don't want to write it that you can repeat it this. So again, you will have this coefficient here, multiply to sigma n 0 to infinity, zn plus 1, beta n plus 1, 5 over 2, 3 over 2, 3. And take a 0 to infinity, t 3 power 3 e minus t dt. What is that? This is a gamma 5 over 2. Need to know the definition of the gamma a few minutes before. So that's 3 over 2 gamma 3 over 2. 3 over 3, 1 over 3 gamma p. Gamma 1 over 2. So you remember it was gamma, so 3 radical p over 4. Finally. and you replace it that here, you have these numbers here, and change it from the 0 to 1 to 0 to infinity to from 1 to infinity. You will find 1 over lambda cubic GA 5 over 3Z. This is a pressure. Okay? Pressure over KT or pressure? Pressure over KT. So pressure over KT finally will be 1 over lambda cubic G 5 over. So you have the equation for the N, you have the equation for the P. So, and I want to talk about the case when I don't calculate the heat capacity or something like that, because you needed to take the derivative of this function. Just you can find it in detail in the book, just 1 or 2 page. They calculated for you the heat capacity, they calculated for you the internal energy, the U and everything, just by derivative of them. So what we find is that we find that N minus N0 over V is 1 over lambda cubic. What is the Z? So we always talk about the ideal gas, ideal gas, ideal gas, but this is not the ideal gas. This is a non-interactive quantum bosonic gas. It's completely different from the ideal gas. So you expected that the equation of a state will be different from PV equal to nRT or PV equal to nRT. And that's really different. Let me to see, lambda is proportional to T minus 1 over 2 if you write the definition. So 1 over lambda cubic is proportional to T3 over 2. So you have a one free parameter, the mu. If you eliminate the mu between these two equations, you can find the equation of the state. If Z is very, very smaller than 1, actually if Z is near to 0, you remember that what was the Z? Z was N01 plus N0. If the N0 is less than what and the N, and this is the case which is not critical, it's a normal case. Normal case is that the number of the particles sitting in the ground state is always low than the total number. Critical case is when the situation reverses, but this is a normal case. In normal case, when Z is very, very smaller than 1 and N0 is very, very tiny number, you can see that here I can forget about the N0. So N over V will be approximation when Z tends to the 0, what is the G? You see that from the definition of the G, G in mu Z, when Z tends to the 0 is 1. It was a sigma, so you keep it just the first time. So from here you can see that only in this case, PVE will be a N-T, as you see. So, and when happened that, when you have Z tends to the 0, do you know? Z is E minus beta mu. Huh? I want to have this 0 tends to the 0. Yeah, the very, very low minus times temperatures. So this is so ideal gas is approximation only for here. I don't need it to write. The other situations we don't know. For another regime, when Z is between 0 to 1, it's actually hard to find the equation of the states. What you will need to do is